This is Dr. Reed, and welcome to the Chapter 14 analysis video on the one-way or one-factor ANOVA. In this video, I will cover the following: ANOVA definition and assumptions, ANOVA concept and formula. I will do a Jamovi ESCI example analysis and interpretation, and finish with a summary slide. Let's begin. ANOVA definition and assumptions. The single factor one-way analysis of variance, ANOVA, is an extension of the independent group's design whereby the means of more than two independent groups are compared on a continuous dependent variable, interval or ratio, across levels of a categorical IV. For example, a teacher wants to examine math quiz scores, DV ratio level, for students with low, moderate, and high levels of anxiety, categorical IV. If the dependent variable is ordinal, the Kruskal-Wallis one-way ANOVA is the best choice. A one-way ANOVA has the following null and alternative or research hypotheses. The null hypothesis states that mu1 is equal to mu2 is equal to mu3, etc. And it says that all group means are equal to each other. The alternative hypothesis, or the research hypothesis, states that at least one group mean is different from the others. The assumptions for the ANOVA. Number one, the scores are independent of each other. This means that the responses or data points are not related to each other in any way. The group distributions are approximately normal. The group variances are approximately equal, and you can use several tests to determine this. You can use the homogeneity of variance test. There's one called the F-max test, which I'll mention in a subsequent slide. The data are interval or ratio level as a strict assumption, to include possibly ordinal as a relaxed assumption for this one. Or if the data are ordinal, you can use the Kruskal-Wallis one-way ANOVA. And then finally, an additional assumption, if you will, is that there are no outliers in any of the groups that are being compared. Let's talk a little bit now about the single factor ANOVA, the concept and the basic formula for the procedure and the statistic. So imagine you have some groups that you want to compare. So I'm showing here sort of a picture of three different groups with three different distributions. So there's a group here on the left here that has a mean of 15. Then the next group, if you go towards the middle here, group number 2 would have a mean of 25 right here. And then the last group over here has a mean of 30. You can also see that the distributions around each mean for the different groups are a little bit different. For example, this middle group here has a much narrower distribution than the other two groups. So for example, its standard deviation would be lower or smaller. So there's the mean of group 1, the mean for group 2 at 25, and the mean of group 3 at 30. So in order to talk about the ANOVA procedure and how the F statistic is calculated, we have to consider we need an anchor point to look at the variability of the individual group means. And in order to do that, we have to have sort of like a stake point, which is going to be the mean of the means, or the grand mean. And that value in this case is 23. So if you take 15 plus 25 plus 30 and divide it by 3, you get a value of 23. And that's called the grand mean, or the mean of the group means. So this is important because we're going to look at the variability in the data. That's why this procedure is called ANOVA, which stands for analysis of variance, or the variability of the groups. And in order to look at the variability of the groups, which means the group means, we have to have a value to compare them to. And that will be the grand mean that you see in front of you. So, first thing you're going to do is you're going to quantify the deviation of group means from the grand mean. So you would do the following. For each group, you compute the difference between the mean and the grand mean, square it, then multiply that value by the group n. Next, you sum these group quantities to get what's called the sum of squares, which means the sum of squared deviations. So this is the sum of squares between, meaning between the means, or between the groups, abbreviated as SS between. Okay, so sum these group quantities to get the sum of squares between, SS between, and then divide that value by k minus 1 to obtain the mean square between, or MSB. So k minus 1, k is for the number of groups that you have in your analysis. So in this case, that would be 3 minus 1, which is 2. And so that would give you this quantity called the mean square between. And that it forms the numerator of the F statistic. So I've got everything kind of coded in colors here. So for the blue, if you look down below here, what we're doing is we're looking at the difference between this mean value here of 15 and the grand mean of 23. And then we're looking at the difference between the mean of 25 and 23, as you see in the arrow here. And then this arrow here would be the deviation, or the difference between the third group mean of 30 and the grand mean of 23. So mathematically, you would follow the procedure that I've outlined up above here, but you can kind of see it in a picture if you look at this picture down below. So we're trying to quantify the deviations of each group mean from the grand mean. And that'll give us the numerator of our F statistic, or F ratio. So the F ratio, the numerator here will be the MSB, or the mean square between groups, and that can also be called the group or the treatment effect. The next thing you need to do is to get the denominator for the F ratio. So to do that, you want to quantify the deviation of the X scores from the individual group means. So you would do the following. For each group, you would take the difference between each X score and the mean, square it, and add those values together. Sum the totals of each group then to get the sum of squares within, which is abbreviated SS within. Sometimes that's going to be SS error too, but we're going to call it SSW, or SS within the group. Then you divide the SSW by n minus k to obtain the mean square within. So in this case, N is the big N, so it's the total number of observations that you have for all the groups combined, and then you would subtract that by the number of groups that you have. And so what that's going to look like, if you look at the diagram again, I have that in red. Now we're looking at the deviation of the X scores around each group's mean. So you would be looking at something like this for the first group, and then like this for the second group, and then for the third group, we're looking at the variability of those X scores around that individual group mean. And so what that is going to be the denominator of the F ratio. So that's the MSW, or within or error. And so what we end up with then is we have what you could conceptually consider to be sort of like a signal to noise ratio. Because when you carry out an ANOVA procedure, like in particular like a one-way ANOVA, what you're interested in is the whether or not there is a group or treatment effect on the means. But we have to consider the variability in each group in order to do that, and that's the denominator. And so in an ANOVA procedure like this, the variability of the X scores around each individual group mean is in a way considered to be sort of error, if you will, okay? And so if you divide those two quantities, if you take the MSB divided by the MSW, you get the actual statistic, which is called the F ratio. And so that value then quantifies the signal to noise ratio. So that gives you a little bit of a concept now of what this procedure is doing. So let's take a look at an example with some actual numbers that I did in Jamovi. So here's an example of a one-way ANOVA in Jamovi. So that just kind of came up with a scenario and put some data in there and then conducted a one-way ANOVA. So let's say, for example, you have participants, n equals 176, were randomly assigned to one of four 10-minute conditions: low, moderate, or high stress, or a no stress control. So there were an equal number of participants in each of the four groups, so that gives us an n, a lowercase n, of 44 per condition, or per group. Systolic blood pressure, SBP, was measured at the end of each condition. And the literature shows that even low levels of stress can raise systolic blood pressure. So now we want to look at this for a second and ask ourselves, what are our variables here? So the first thing you want to do is, what is being assessed in this example? What is being measured? The answer is that what's being measured is systolic blood pressure. And that then becomes the dependent variable in this example. And then our independent variable, if you will, it's a categorical independent variable. And there's just one of them that has 4 levels, and that would be the level of stress. That's why we're calling it a one-way ANOVA, or a single factor ANOVA. So our dependent variable is systolic blood pressure. That's what's being measured. But we have a categorical independent variable here, and that is our level of stress. And there are 4 levels: low, moderate, high, or no stress. So let's take a look at the data setup now over here on the right-hand side. and we'll lay that out for you. So there's a abbreviated list showing the ID values from 1 all the way. It's going to go up eventually to 176. Then we have the stress level, none, low, moderate, and high, and then the systolic blood pressure that's measured. So we have our subjects here in the first column, our factor or our categorical independent variable, and then the dependent variable. So this is the way that most computer programs have you arrange your data in order to conduct a one-way analysis of variance. So this middle column here, the stress level, is important because by having these names of these different groups in here, this way the computer knows which values over here on the right for the systolic blood pressure belong separately to these different groups that you have. So it will calculate the means and calculate the F ratio for us. So there's the first group, that's the none, that goes 1, 2, 3, dot, 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 up to 44. Then the next group there starts at 45, go all the way up to 88 for the low, and then the moderate would start at 89 and go all the way to 132, and then the last group would start at 133 and go all the way up to 176. So you would just put that information into Jamovi, and then in Jamovi you would do the following. So you have your data in Jamovi, and then just in the analysis tab in Jamovi, you would just go to ANOVA and select the one-way ANOVA, and then you have that dialog box with the variables in it, and so you bring in the variable for the systolic blood pressure, bring that over as the dependent variable, and then the stress level variable, that becomes the grouping variable. And then down below, so now you have your variables set up, and so then you can choose different options. And so you can check the box here for, we can go ahead and assume equal variances for these groups, and then you can check that. You can also not assume equal variances, but for this example, we'll assume equal variances between the groups. And then you can check the descriptives table to get the descriptives for each group, and we can also get a descriptives plot, which is also kind of nice because it will give us the groups with 95% confidence intervals. And then in ESCI, we can add then to the Jamovi output. So in ESCI, after you get the output for the Jamovi, you can go to the ESCI module, and in there you go to means and medians, and then select independent groups contrast. And that'll allow us then to make our contrast that we want. And if you look back up above in the paragraph up here for the example, I state that the literature shows that even low levels of stress can raise systolic blood pressure. So we'll go ahead and conduct a contrast that just compares 2 of the 4 groups with each other. And so what we'll do is we'll compare the low stress with the control group or the no stress group. So in ESCI, once you select independent groups contrast, then the systolic blood pressure is the outcome variable, okay, which is the same thing as the dependent variable. And then the stress level, again, will be your grouping variable. Once that's in there, then it gives you a couple of boxes to type in your contrast. So we want to define our contrast, and the reference will be the none, and the comparison you would type in the word low. And once you do that, you'll get the output for the ESCI. So let's take a look at the output. So the Jamovi output then, first thing that we have is the results of the one-way ANOVA procedure. And it says one-way ANOVA, and then it has in parentheses Fisher's. And this is where you assume equal variances. And so that's the technique that Fisher developed for the one-way ANOVA, is to just basically assume equal variances. And we will see that for this example that the variances are basically equal. In other words, that assumption has been met for this one. So the output shows that there's your dependent variable, that's your systolic blood pressure. There's the F statistic right there. That's our signal to noise ratio. Okay? And what that's that's our observed F ratio, and we would be able to look up or have the computer tell us what an appropriate critical F ratio would be. And we would look that up at 3 and 172 degrees of freedom. We get a particular value that we either meet or exceed. And the computer then tells us, assuming the null is true, how far our F ratio that we observed exceeds or does not exceed, if you will, the critical value for the 0.05 level of probability. So we have an F ratio of 69.4, and the probability of observing a value of 69.4 or greater, assuming that there's no differences in the means between any of the four groups, that probability is less than 1 in 1,000. And so typically we only need to have a probability level of less than 5% or less than 5 in 100 to claim probability evidence against the null hypothesis. So we appear to have a situation where our data show that there's at least one or more groups that appear to be statistically different from one another. So let's look at that little diagram then that you get, and this gives us, this is in Jamovi, by the way, still. So this gives us the little diagram we want to see. There's our stress level on the x-axis, none, low, moderate, and high, with the systolic blood pressure or the dependent variable, as usual, on the y-axis. And so the systolic blood pressure is measured usually in millimeters of mercury. So we don't have the units up there, but that's what that is. And you can see that we have the means of each group with their corresponding 95% confidence interval. You can clearly see there that as the stress is going up, the measured systolic blood pressure on average is going up. And for our comparison, we want to compare the none or no stress with the low stress group. And so from the textbook, hopefully what you've learned so far is if you examine these two confidence intervals, you can see that they do not overlap at all. In other words, the upper value or the upper limit for the none condition in terms of its systolic blood pressure, that upper limit value is lower than the lower limit for the low stress group. So there's no overlap here between these two intervals, and that's a very good indication that we have a statistical difference between those average systolic blood pressures. Let's take a look at the ESCI output now and see what that tells us. So here's the ESCI output, and here we just have our nice little descriptive table from the results. We have our dependent variable of systolic blood pressure and a total N of 176 with a 44 in each group. There's our stress level, none, low, moderate, and high. We're giving our mean. There's our mean systolic blood pressure, the standard deviation, and the confidence interval for each group. So it's a nice table. So for when you do your research study for your dissertation, you definitely in some way want to have a simple descriptive statistics table that looks something like this, that gives the readers the groups that you have, the means of the groups, the standard deviations, and the confidence intervals. Very important, simple statistical information that carries a lot of uh, good information for people to see. If you remember from last semester, I mentioned at some point in time that if you report means, you always want to report standard deviations, because means and standard deviations go together. They go together to give the reader a description of the distribution for that group, for example. If you just give the mean without the standard deviation, your analysis is incomplete. So always remember that the means and standard deviations, they go together to give the reader the complete information. So what we're going to look at is we're going to look at those first two right there, the none versus the low. So let's take a quick look at that. You see that the mean is 121 versus 130 for the low, about a 9 millimeter of mercury difference there on average. And then if you go over to the right and look at those confidence intervals, you can see that they do not overlap. In other words, the lower limit for the low stress group at 127 is higher than the upper limit for the none group. So right there, that's how you kind of eyeball this. You see that 127 here, and you see the 124 here. So that means we have a complete separation between those two confidence intervals. And once again, when you see that, that's a good indication that there's a statistical difference between those means. So then the next table that shows is the little bit more of a breakdown there for that mean difference for the contrast. So let's look at that. So you see this mean difference table that ESCI gives us. So there's the dependent variable, systolic blood pressure, and the effect is the low minus none, and we get 9.76. So that is the means subtracted from one another. So if you look up at the table up here, and again, this is rounded, but we take that 130 and the 121, we've taken the difference between the means for those two groups, and we get a value of 9.76. And then the confidence interval for this difference is located right over here on the right. So let's look at that real quickly. The first question you ask yourself is, where is the null hypothesis here? Or what is the null hypothesis? Well, the null is that the difference between the two groups is 0. Because remember, if you have two groups that have exactly the same mean, when you subtract the means from each other, you get a value of 0. That's the null. So the first thing you do is you look at this here and you say, is 0 in that interval? And clearly 0 is way outside that interval, right? So a zero difference, i.e. the null, is clearly not a plausible outcome here. So this is just giving us another visual piece of information regarding this contrast. And of course, your analysis would not be complete if you didn't include an effect size. So let's look at the table for that. And that's right down below here. That's our standardized mean difference, or our D value effect size, which you're a little bit familiar with now. So we have our dependent variable. The stress level effect, again, is the low minus the none. But what we're doing now is we're standardizing that difference. So what we've done here is we've taken the mean difference of 9.76 and we're dividing that by a standardizer, which is going to be the pooled standard deviation between the two groups being compared. And when you do that, you get this value of 0.96. 0.96. And then there is the confidence interval for that D. We also include there's the biased value and the unbiased value. But once again, our sample is relatively, we've got two samples of 44 apiece here. So you can see that, as I've mentioned several times, unless the samples are down around 20 or less, you're not going to see much difference between the biased and the unbiased. So there's our effect size, okay? So we see that we have a separation, a larger mean effect on the systolic blood pressure for the low compared to the none, of a difference of about 0.96 of a standard deviation in the population. And if you recall from previous chapters or previous analysis videos, I've gone through the rating scales for Cohen's D a couple of times, and a 0.96 is a very good size effect. Most authors would rate that as a large effect. In other words, this effect is large enough so that it would be noticeable and very likely to be meaningful in the real world in a practical sense. So let's interpret these results now. And we haven't done too much of that, but let's start with this, and this will give you an idea of how you might interpret the results that we just went through. So I'm going to start out with the interpretation with the ANOVA and then move and make it more for the comparison that we did, or the contrast. So interpretation. For the ANOVA, an F of 69.4 occurs less than 0.1% of the time in random sampling. P is less than 0.001. And P is less than 0.001 is markedly less than the 0.05 criterion, and thus provides probability evidence against the null. The average systolic blood pressures ranged from 120.72, standard deviation 10.88 for the no stress condition, to 151.2, standard deviation 10.05 for the high stress condition. For the no stress versus low stress contrast, group mean 95% confidence intervals do not overlap. The group mean difference of 9.76, 95% confidence interval 5.5 to 14, shows that a zero difference is not plausible and highly improbable. The D of 0.96, 95% confidence interval 0.53, 1.39, shows that the low stress mean systolic blood pressure was 0.96 standard deviation units greater than the no stress mean systolic blood pressure. A large effect by most criteria. And I've given the authors here: Cohen, Thunder, Saw-Wilowski, 2009. Now I want to add a little bit more about that D. So here's a couple of statistics. One is the probability of superiority that I mentioned earlier in the semester. There's also another one here that I'm going to mention. Let me go ahead and read through this first. A D of 0.96 also means there is a 75% chance a participant picked at random from the low stress group will have a higher systolic blood pressure than a participant picked at random from the no stress group. Okay, that right there is the computation and interpretation for the probability of superiority. And then this last one here is what's called Cohen's U3 subscript for the 3. And what that tells us is the number of subjects in this case, in the low stress group that would have a higher systolic blood pressure than the mean of the no stress group. In this case, that would be, and that 83% of subjects in the low stress group have a systolic blood pressure above the mean of the no stress group. So these last two sentences, the last sentence here, I'm doing the probability of superiority. This is in reference to the D value. I'm doing the probability of superiority, and I'm also doing another calculation that can be done so that the readers can get a good handle on the meaning of your effect size. Because if you go back to this sentence here, the D of 1.96, 95% confidence interval 0.3, 1.39, shows that the low stress mean systolic blood pressure was 0.96 standard deviation units greater than the no stress mean systolic blood pressure. That part right there, most people have trouble understanding what that entails. In other words, because what we have here is a mean difference in standard deviation units, right? And that's what it is. It means that one group's mean is 0.96 standard deviation units greater than the other group's mean. And most readers, or many people, have difficulty understanding what that means in terms of like an inference to the population level. And that's a fair assessment. And so therefore, a lot of researchers have come up with other calculations that you can make regarding your D effect size so that people can have a alternative way of conceptualizing that D and understanding it. And that's what the last part of this paragraph is saying. And that's where the probability of superiority comes in, and also the Cohen's U3 statistic. So make sure that you are aware of that if you calculate D's and effect sizes in your research study. So, in sum, the findings provide ANOVA probability, mean difference, 95% confidence interval, and D-value evidence of a clear statistical meaningful difference between the average low stress systolic blood pressure, 130.48, and the average no stress systolic blood pressure, the mean of 120.72. So if you notice in this last summary here, I'm giving the reader all of the lines of evidence that point to that statistical difference. We have probability evidence from the ANOVA procedure in general. We have mean difference evidence, 9.76 millimeters of mercury difference. We have confidence interval evidence, meaning that our zero null hypothesis value for the difference between the two means is clearly not in that interval. And finally, we have clear d-value effect size evidence for that statistical difference between those two groups. So that's how you would summarize your results from this, along with any tables and figures that you might have. So let's go ahead and hit that summary slide. So let's summarize the one-way single factor ANOVA. The single factor one-way analysis of variance is an extension of the independent group's design, whereby the means of more than two independent groups are compared. Single factor ANOVA assumptions include independence of observations, approximately normal distributions, approximately equal group variances, interval or ratio level data, and no outliers. The one-way ANOVA null hypothesis states that mu1 is equal to mu2 is equal to mu3, etc., meaning that all group means are equal. And the alternative or research hypothesis is that at least one group mean is different from the others. The F-ratio statistic for the ANOVA procedure can be conceptualized as a signal-to-noise ratio. The ANOVA procedure includes the F-ratio, independent groups contrasts with 95% confidence intervals. Typically, that contrast is planned in advance, and the computation of effect sizes, such as d-values, with corresponding 95% confidence intervals. And that takes care of that analysis video. There will be a 5-point quiz for that. That'll be posted up on Brightspace as usual. If you have any questions about this analysis video, please send me an email. Thanks for watching.